In 1970, the most powerful mathematician alive stood up, walked out of the room, and never came back. He didn't retire. He didn't slow down. He simply decided that mathematics, the thing he had reshaped more profoundly than anyone since Euclid, was no longer something he wanted to be part of. His name was Alexander Grothendieck. And this is the story of a man who didn't solve problems. He dissolved them. Grothendieck's childhood reads like a novel written by someone who doesn't believe in mercy. Born in Berlin in 1928 to a Russian anarchist father and a German journalist mother. Both were political radicals. When the Nazis consolidated power, his parents fled to France. Young Alexander was left behind with foster families. He was 5 years old. Eventually reunited with his mother in France, the two spent the war years in internment camps. Vichy France was not kind to stateless refugees. His father, Alexander Shapiro, was deported to Auschwitz and murdered there. By the time the war ended, Grothendieck was 17, stateless, effectively orphaned, and already teaching himself mathematics from textbooks he found inadequate. Not inadequate because they were too hard. Inadequate because they didn't go deep enough. At university in Montpellier, Grothendieck's professors gave him a set of problems. He solved them, found them unsatisfying, and then independently redeveloped the entire theory of Lebesgue measure and integration. From scratch. On his own. Without knowing it already existed. This was a body of work that had taken generations of professional mathematicians to construct. He just rebuilt it because he thought it should be there. His professors in Montpellier realized they had nothing left to teach him, and sent him to Paris. At the Sorbonne, surrounded by the greatest mathematicians in France, people like Henri Cartan and Laurent Schwartz, the establishment didn't just see talent. They saw something stranger. A completely different way of looking at mathematics. Not sharper tools. A different workshop entirely. His subject became algebraic geometry. The study of shapes defined by polynomial equations. A circle is x squared plus y squared equals 1. A parabola is y equals x squared. An ellipse, a hyperbola, a cubic curve. These are the simplest objects in algebraic geometry. But the subject asks a deeper question. What if the numbers aren't real numbers at all? What if the equations live over entirely different number systems? Over the integers, over finite fields, over bizarre algebraic extensions nobody has named yet? Before Grothendieck, algebraic geometry was a landscape of clever techniques and hard-won specific results. A collection of islands, each proved individually, with boats ferrying ideas between them when someone was clever enough. After Grothendieck, it was a continent. A single, unified theory built on foundations so abstract that most working mathematicians needed years just to read the definitions. He didn't add new islands. He raised the sea floor. His central invention was the scheme. In classical algebraic geometry, you study a shape by looking at its points. The circle has points. You can count them, measure them, touch them. Grothendieck said this was thinking too small. A scheme is a geometric object built not from points in space, but from the algebraic structure of equations themselves. Consider the equation x squared equals 0. In ordinary geometry, the solution is just x equals 0. A single point. But Grothendieck said x squared equals 0 is not the same thing as x equals 0. The squaring carries information. It remembers a direction. It remembers a tangent. He built an entire geometry that could see the difference. Points that look identical in ordinary geometry become entirely different objects in his framework, carrying hidden structure like invisible threads attached to a location. These were called nilpotent elements. And they turned out to be not a curiosity, but the key to unifying number theory and geometry into a single language. Grothendieck had a philosophy about mathematical problem solving, and it explains everything about how he worked. He called it the rising sea. Most mathematicians, he said, attack a hard problem like a nut. They look for a crack. They hit it with a hammer. They find a clever trick, a sharp tool, a specific insight. And sometimes the nut splits open. Grothendieck's method was different. He would not attack the nut at all. Instead, he would slowly, patiently, raise the level of theory around the problem. Build definitions. Build abstractions. Build vast oceans of structure. And eventually, the water rises so high that the nut is submerged, and the shell softens, and it opens on its own. He didn't solve problems. He built frameworks so powerful that problems dissolved. This sounds mystical. It was devastatingly effective. The rising sea took physical form. Starting in 1960, Grothendieck ran legendary seminars at the Institute for Advanced Scientific Studies, outside Paris. These seminars produced thousands of pages of mathematics. The elements of algebraic geometry, known by the French abbreviation EGA, ran to over 1,500 published pages and was never finished. It was intended to be 13 volumes. 4 were completed. The seminars of algebraic geometry, the SGA, added several thousand pages more. His students and collaborators, many of whom became leading mathematicians themselves, spent decades filling in the details of ideas he had sketched out in afternoon conversations. He would describe an entire theory over lunch. Someone else would spend 5 years writing it down. In 1966, Grothendieck was awarded the Fields Medal, the highest honor in mathematics. He had built the machinery that made the Weyl conjectures provable. These conjectures connected number theory to geometry through the counting of solutions to equations over finite fields. His student Pierre Deligne would complete the final proof in 1974, using tools Grothendieck had forged a decade earlier. Through a single cohomological framework, called Atali cohomology, Grothendieck had unified entire branches of mathematics that had previously seemed unrelated. He was, by broad consensus, the dominant intellectual force in mathematics for the entire decade of the 1960s. No one else was close. And then, at the height of his powers, he stopped. It began with politics. Grothendieck discovered that the IHES had received partial funding from the French military. He resigned. Immediately. Without negotiation. He had survived the camps as a child. He would not work in an institution that took money from armies. He became an environmental activist, co-founded a group called Survivor at Viva, Survive and Live, and took a teaching position at a small university in Montpellier. Then he withdrew further. He wrote a massive autobiographical manuscript called Récoltes et Semis. Harvesting and Sowing. Over 1,000 pages. Part mathematical memoir, part spiritual confession, part furious reckoning with colleagues he felt had stolen, buried, or misattributed his ideas. He sent it to mathematicians around the world. Most didn't know what to make of it. Some called it a masterpiece. Some called it paranoia. Most just called it long. In 1991, Alexander Grothendieck disappeared. He moved to a small village called Lassa in the foothills of the Pyrenees, and cut off nearly all contact with the outside world. No phone. No email. No visitors, except a handful of people he trusted. He reportedly spent his final 2 decades writing tens of thousands of pages of private meditations on mathematics, spirituality, and the nature of dreams. Some estimates say 20,000 pages. Others say more. He had turned inward completely. The man who had rebuilt algebraic geometry from the ground up was now building something else entirely, and he was building it for no audience at all. When he died in November 2014, at the age of 86, the pages were left to his children. A mind that had reshaped how humanity understands space, number, and form spent its last decades speaking only to itself. But here is what matters. Grothendieck's mathematics didn't stop when he did. Schemes are now the foundational language of modern algebraic geometry. Every graduate student in the field learns to think in his framework. Italian cohomology, his invention, was the essential tool in the proof of Fermat's last theorem by Andrew Wiles in 1995. The Grothendieck group appears in string theory. Category theory, which he elevated from a bookkeeping device into a foundational language, now shapes computer science, mathematical logic, and theoretical physics. The rising sea he built is still rising. 50 years after he walked out of that room, mathematicians are still finding problems whose shells dissolve in frameworks he created before most of them were born. He wanted to leave mathematics behind. Mathematics did not return the courtesy.